You know, every single day, there's this invisible guardian protecting your most sensitive digital information. It's a piece of tech so fundamental, you probably use it hundreds of times without even realizing it. So today, we're going to tell its story, the story of elliptic curve cryptography. I mean, seriously, stop and think about that for a second. When you send a private message, or buy something with a credit card online, or even just check your crypto wallet, what is actually stopping the entire world from peeking over your shoulder? Well, for the most part, the answer is this incredible, elegant piece of mathematics. Okay, let's get into it. So for a long, long time, the king of the castle was an encryption method called RSA. And look, it's strong, but to get that top-tier security, you needed these massive 3,000-bit keys. They're just way too slow and clunky for the little computers in our phones or smartwatches. And then, back in the mid-80s, a new hero shows up, ECC. It gives you the exact same level of security, but with a tiny little 256-bit key. It's just smaller, way faster, and so much more efficient. So what's the secret sauce? What makes ECC so darn efficient? Well, unlike the older guys like RSA, which were all based on the nightmare of trying to factor gigantic numbers, ECC security comes from a totally different place. It's all built on the really unique and elegant math of something called elliptic curves. That foundation is the key to all its power. It all boils down to one core math problem, the elliptic curve discrete logarithm problem, or ECDLP for short. You can think of it as a perfect trapdoor function. It's a calculation that is super easy to do in one direction, but trying to reverse it, it's practically impossible for a computer to do. That mathematical one-way street is what's keeping all your secrets safe. Okay, let's try a simple analogy to see how this trapdoor works. Imagine there's this weirdly shaped curve, and everyone agrees on a public starting point on it. Now, your private key, that's just a secret number that only you know. Let's say it's the number of hops you're going to take along the curve from that starting point. So you do your secret number of hops, boop, 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 and you land on a new point. That final destination, that's your public key, which you can share with the world. Here's the magic. Even if someone knows where you started and where you ended up, they have no way of figuring out how many secret hops you took to get there. That's the ECDLP in action. Pretty cool, right? And because it's so lean and mean, ECC is literally everywhere. See the little padlock in your web browser? Yep, that's ECC securing your connection. The signature that authenticates every single Bitcoin or Ethereum transaction? That's an ECC algorithm. Your private iMessages and WhatsApp chats? You guessed it, end-to-end encrypted with ECC. It is the invisible workhorse of our entire modern digital world. So the math behind ECC is rock solid. I mean, the ECDLP is considered unbreakable by any normal computer we have today. But here's the thing. Any system is only as strong as its weakest link. And in the world of cryptography, that weak link is almost always us, human error during implementation. See, when you use ECC to create a digital signature, the process uses a secret random number called a nonce. And there is one rule, one single golden, absolutely critical rule you have to follow. You can never, ever reuse a nonce. It has to be totally fresh and completely random for every single signature you create. Because if you break that one rule, the whole house of cards comes tumbling down. If a programmer gets lazy or just makes a mistake, and the same nonce gets used to sign two different messages, well, an attacker can just grab those two public signatures. Then, with a little bit of algebra, I'm talking like high school math here, they can literally cancel out the shared nonce in the equations and solve for the one thing that was supposed to be secret forever, your private key. It's not a guess, it's not a brute force attack, it's pure mathematical certainty. And this isn't just some textbook theory. Oh no, this happened big time. Back in 2010, Sony's developers made this exact mistake. They used a static, non-random nonce for signing software on the PlayStation 3. Hackers figured it out, used that two-signature trick, and poof, they calculated the console's master private key. The key got posted online, and just like that, the PS3's entire security model was completely shattered. It blew the doors wide open for piracy and all kinds of custom software. So we've learned to be a lot more careful about how we implement this stuff. But ECC's story isn't over. In fact, its greatest challenge is still on the horizon. A threat that doesn't care about sloppy programming, because it attacks the very mathematical heart that makes ECC strong in the first place. I am talking, of course, about quantum computers. The clock really started ticking way back in 1994, when a mathematician named Peter Shor figured out that a theoretical quantum computer could solve that impossible ECDLP problem easily. This has led to this terrifying new strategy called harvest now, decrypt later. Basically, adversaries are just sucking up and storing all our encrypted data today, knowing that in the future, they'll have the quantum keys to unlock it all. And that future is getting closer fast. A lot of experts are pointing to around the year 2030 for what they call Q-Day, the day a quantum computer can actually break our current encryption. And look, this isn't science fiction anymore. We can actually calculate what it would take. To crack a standard 256-bit ECC key, a quantum computer would need about 2,330 stable qubits. Now, we aren't there yet, but the progress in quantum computing is moving at a blistering pace. This is a very real and very quantifiable threat. So, is that it? Is everything doomed? Not at all. The good news is, the cryptography community saw this freight train coming from a mile away and has been preparing for years. We are now officially entering the era of post-quantum cryptography. The U.S. National Institute of Standards and Technology, NIST, ran this massive multi-year competition to pick a new set of standards that are quantum resistant. These new algorithms, with cool names like Kyber and Dilithium and Sphinx Plus, are based on totally different kinds of math problems, things that we believe are incredibly hard for both normal computers and quantum computers to solve. These are the new guardians, getting ready to take over. Now, we can't just flip a switch overnight. That would be chaos. So the strategy is what's called a hybrid approach. For a while, our systems are going to use both ECC and one of the new post-quantum algorithms at the same time. That way, you get the best of both worlds. You're protected from quantum attacks, but you're still compatible with all the older systems. It's how we build the new, safer bridge without closing the old one down. Elliptic Curve Cryptography has been an absolutely remarkable guardian for our digital world. It's been elegant, efficient, and strong, but its time on the throne is coming to an end. We have the new tools, we have the roadmap for a secure post-quantum future. The only question left is whether we can get there fast enough before that quantum clock finally hits zero.